Alright, so we are talking about cycle notation. Here are two permutations whose cycle notation we wrote down. Beta is an element of S6. In the longer notation it looks like this, but in the more abbreviated cycle notation it looks like this. So what it tells you is that beta takes 1 to 3, 3 back to 1, and then it permutes 2, 5, 6, 4 in cyclical manner. So beta of 1 is 3, beta of 3 is 1, beta of 2 is 5, etc. That's what that notation tells you. One thing that the cycle notation is good for, we saw, is that it lets you calculate the order. We define something called the type of a permutation, or the cycle type. This one has cycle type 4, 2. This one has cycle type 4, 3, 1, 1. You throw in the cycles of length 1 as well. And then the order is the least common multiple of the cycle types. So these numbers, I mean. So like this one has order 4 because it's the LCM of 4 and 2. This one has order 12. Another thing that the cycle notation is really good for is calculating conjugates. Remember, a permutation of the form tau sigma tau inverse is called a conjugate of sigma. So sigma and sigma prime are conjugate if you can write sigma prime as tau sigma tau inverse for some tau. So what this lemma is saying is that if you know the cycle notation for sigma, you can write down the cycle notation for tau sigma tau inverse pretty quickly. And let's check that for an example. I don't know. Let's take this beta maybe. So rather than proving the lemma, we'll just illustrate it in an example, which I think says a lot more. And let's take another permutation of 6 letters, I don't know. Maybe 1, 2, 6. And then 3, 4. Okay. So these are two elements of S6. Let's calculate tau, beta, tau inverse. What I want to calculate is what happens to tau 1 when I apply this. So when you apply tau, beta, tau inverse, you're applying, so this is some number, right? Tau 1. In this case, it happens to be 2. Tau of 1 is 2. Right. So when you apply tau, beta, tau inverse, first you apply tau inverse. Apply tau inverse to tau 1, goes back to 1. Then you apply beta, goes to beta 1. Then you apply tau back to it, so goes to tau of beta 1. So you see, beta sends 1 to beta 1, so tau beta tau inverse sends tau 1 to tau beta 1. What is beta 1, by the way? It's 3. So it would send tau 1 to tau 3. So because beta sent 1 to 3, this element sends tau 1 to tau 3. So if I wanted to write tau beta tau inverse, it would go tau 1, tau 3, and for the same reason tau 3 is going to go back to tau 1. It's close. And then similarly, tau 2 will go to tau 5, will go to tau 6, will go to tau 2, will go back to tau 6, tau 4, and it would go back to tau 2. So tau beta tau inverse is actually going to be the permutation. What is tau 1? Let's look at tau, and I can write all these things down. Tau 1 is 2, tau 3 is 4, and then tau 2 is 6, tau 5 is 5 because there's no 5 here, tau 6 is 1, and tau 4 is 3. So you just calculated tau beta tau inverse without actually multiplying the permutations, just by looking at how things move around. And this is rather powerful. So more generally what I'm saying is that if you have I and j and beta sends I to j, then tau beta tau inverse is going to send tau I to tau j. Because when you apply tau inverse, it goes to I, then you apply beta, goes to j, and then you apply tau, goes to tau j. So this is why. So the observation is, if beta sends I to j, then tau beta tau inverse sends tau I to tau j. And this thing follows from that. Okay, so that's all I'll say about this lemma. In fact, there's more. Two things are conjugate if and only if they have the same cycle type. So this is saying that they have the same cycle type. Beta has cycle type 4, 2. Tau beta tau inverse also has cycle type 4, 2. But this is actually if and only if. Let's leave this. The next topic is to find nice generators for Sn. So generators. For this, we first need to introduce transposition. A cycle of length 2, or a 2 cycle, is called a transposition. So like 1, 2 is a transposition. So is 3, 5. This is written in cycle notation. So general one looks like ij. Flips I and j and leaves everything untouched. Sometimes I call them flips. Transposition is too long a word to write. In particular, I want to introduce these transpositions. These are called adjacent transpositions. They flip things that are next to each other. The theorem is that these guys generate Sn, meaning every permutation can be written as a product of these very simple kind of permutations. Not disjoint ones, of course, just a product. So first I want to show that any flip, like ij, can be written as a product of these guys. And that's just playing with this conjugation business. Let's just do that in an example. Like if you give me any flip, say you give me 2, 5, then I say 2 and 5 are kind of far apart. Let's bring them a little closer, 3, 5, and I can do that by conjugating. You see, when you conjugate by 2, 3, all you have to do is replace the 3 by what happens to it when you apply 2, 3 to it. And when you apply 2, 3 to 3, it goes to 2. And when you apply 2, 3 to 5, it goes to 5. So this guy is equal to 2, 5 by what we just learned up here. And by the same token, no, it's 3, 5 is now 3, 4, 4, 5, 3, 3, 4 inverse. But then, of course, these are transpositions, so they're inverses themselves. If you flip twice, you are back to what it is. So 3, 4 inverse is 3, 4, and 2, 3 inverse is 2, 3. And now you have written 2, 5 as a product of these adjacent transpositions. And this can be generalized quite easily. So this shows any transposition is a product of S1, S2, Sn minus 1. Now what remains to do is to prove this claim that any permutation, any sigma in Sn is a product of transpositions, flips. Means the same thing. So once you give me a sigma, if I can write it as a product of transpositions, then I can use this business to write it as a product of adjacent transpositions. So proving the claim is enough. Okay, and this you can prove easily by induction on n. Induction on n equals 1 and 2, you have hardly anything to do because all S2 have is identity and a flip. So that's good. So what goes on is the following. So let's take up example again. Beta, let's take this one, 1, 3, 2, 5, 6, 4. So you give me this guy. And so this is something in S6. So when I'm doing induction, I can assume that I have proved my claim for S5. So I know that anything in S5 can be written as a product of flips. So you give me this guy, it's not in S5 but in S6. But what I can do is I can just fix the last element. See, so where does 6 go under beta? Beta of 6 is 4. Okay. So let's take beta and multiply by 4, 6 on the left. Now where does beta prime takes 6? First you have to apply beta to it, and then you have to apply 4, 6 to it. So this would be, when you apply beta to 6, it goes to 4, and then you apply the flip 4, 6 to it. So that is now 6. So beta prime fixes 6, as we say. It takes 6 to 6. So beta prime is really a permutation of 5 things. If you write it longhand, 6 goes to 6. So it's really just permutes 5 things. So by induction, by our assumption, induction step, so assume claim for S5, right? That would be the induction step essentially. By induction step, beta prime can be written as a product of transpositions where tau 1, tau k are flips. But beta prime is beta times 4, 6. But then you can multiply both sides by 4, 6. 4, 6 is its own inverse, so it goes away from the left and it shows up on the right. And now I have written beta as a product of flips as well. These are already flips, and 4, 6 is also a flip. So this proves the claim. I mean, I just showed it for one element in S6, but this is essentially the argument in induction step. Okay? So that's why Sn is generated by these guys. So the next job is to define a certain... So far the theory of permutation groups is rather straightforward. The next thing is to define something called the sign of a permutation. So this is a homomorphism from Sn to the group of 2 elements plus minus 1. And this would give you a rather special subgroup and a very important subgroup of Sn called An, the alternating group, the group of even permutations. So next time we'll talk about that, and we'll have to introduce a third way of representing permutations for the argument there. We have one way, a second way. Now we'll have a third graphical way of writing permutations.